Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy to understand videos. My name is Ebby, lead tutor for math and political science, and in today's video we'll cover limits and derivatives. Let's get started. So what's a limit? Well, it's like a trajectory, whatever the function is approaching. Here's how we write it. How we actually say it is the limit as x approaches a of the function equals L. So you're approaching along the x-axis towards a specific x value, and then you want to get what the y value is associated with that x value, and you want to see if it exists or not. Now let's take a look at some different ways we can evaluate limits. So limits can be found graphically as well. So number one is not a limit, but an actual evaluation of an x value. So we're looking at f of 2. And we go straight to the x value of 2, and we look up and down to see if there's a closed dot. So going to the x value of 2, we see that there's a closed dot at 1, so we know that the answer for number 1 is 1. For number 2, we do the same thing. We go to the x value of 0, look up and down the x value to see if there's a closed dot, and there is a closed dot at y equals 3. There's an open dot at y equals 5, so we ignore that. Now number 3. The limit as x approaches 2 from the right. That will be equal to 1 because we're taking the trajectory from the right side. So that's going to be the side closest to the asymptote at x equals 3. And we're taking the path towards 2, so we also get 1. And from the left side, we'll be taking the path starting at the open dot at x equals 1 towards 2. And we also get 1 if we go from the left side. And if we could approach the same value from the left and the right side, that means that the limit as x approaches 2 from both sides is also equal to 1. Now, number 6 implicitly asks us to take the limit as x approaches 0 from the left and the right. And if they go to the same number, then we'll have an answer. If they go to different numbers, we don't have an answer. So since the right-hand limit goes to 5 and the left-hand limit goes to 3 at x equals 0, then we know that the limit does not exist. Now let's check the limit as x approaches 3. We're checking from both sides again, and the left-hand limit goes towards positive infinity because there's an asymptote there. And then the right-hand limit goes towards negative infinity. So we know that this limit also does not exist. How do we find limits algebraically? Well, the first thing to do is always let the limit approach. Oftentimes you'll see that the limit will give you does not exist. So you use these 4 methods that are very common: multiplying by the conjugate, factoring or simplifying, combining fractions, or using identities in order to figure out what the actual answer is. So oftentimes you'll use these 4 things in conjunction with each other for a specific limit. Now let's look at a couple examples using these methods. Example 1 here, the limit as x approaches 3 of this function. Letting the limit approach right off the bat by plugging in the x value would give us 0 on the denominator, which means that the limit does not exist. That is not the correct solution though. If we change how the function looks, we will get the correct solution. How do we change how the function looks? Well, for this particular question, we'll multiply times the conjugate of the numerator in order to get rid of that problematic x minus 3. So the conjugate of the numerator looks like this: the square root of x plus 1 plus 2. It needs to be multiplied by the numerator and the denominator. It's like a fancy form of 1. So once you simplify the numerator, you will get x plus 1 minus 4, which is equal to x minus 3. That will cancel with the denominator and leave you with 1 over the square root of x plus 1 plus 2. Now recheck the limit by letting the limit approach 3. Once you do that, you'll get 1 over 4. So the answer to this is really 1 over 4. Okay, second example. So in this case, we see that the function is not factored. So we want to factor it first. And if you're a little bit rusty on factoring, we have a TutorTube video located on our website, learningcenter.unt.edu, called Factoring 101. So check out that video if you need some more help on factoring. So we factored numerator and denominator, and we get this. Now we can clearly see that we can cancel out x minus 2. Then you simplify to this. and now you want to recheck the limit. So you always want to recheck after you do one of the methods. So you plug in 2, and you get 8 over 2, which is 4. So third example here, the limit as x approaches 0 of 2 tan 4x divided by sine 2x. Since this is a trig value, we want to think of an identity to help us solve this. So before we do that though, let's just change the division bar to a division sign. This will become helpful later on when we're trying to cancel things out. So the identity that we need is an identity that will change the argument to be the same. So 4x into a 2x, which would be the double angle identity. So we're going to use a double angle identity for the numerator, which is 2 tan 2x divided by 1 minus tan squared 2x. And this comes from trig identities and trigonometry, which you learned in pre-calc. So now we will plug this back in to the original equation. And remember that we have two 2's being multiplied times each other, so that's where I get the 4. And then we have this. So we're going to use a property of multiplication where we can multiply times a reciprocal and expand everything out. So this is helpful because we're trying to cancel some things out. So now change everything to sine and cosine so that you can start canceling things out. So here's what we have now. And we can see that the leftmost equation cancels out with the rightmost equation first of all. So here's how the function would look after canceling those two things out. So we can combine these two functions and we get this. So now you want to distribute the cosine 2x on the denominator. Once you distribute that, that'll cancel out with one of those cosines on the fraction there, and then you will let the limit approach 0. So we let the limit approach 0 now because we sufficiently changed the function and we can recheck the limit. So once we let that approach 0, using some unit circle values, we get 4 divided by 1 minus 0 divided by 1. So that will yield 4 divided by 1, 4. Example 4, we want to determine the limit as x approaches 0 of this function. We see that there's a fraction on the numerator, so we want to combine that fraction. So the denominator will be 5 times x plus 5. So the numerator for the left side of the fraction will become 5, and the numerator for the right side will become x plus 5. They kind of crisscross. So once you combine those numerators, you will also remember you have to multiply times 1 over x. It's the same thing as dividing by x. And combining those numerators would be 5 minus x minus 5, which gives you negative x divided by 5 times x plus 5. And that negative x cancels out with the 1 over x. So that's why we multiplied times 1 over x. So you get negative 1 divided by 5 times x plus 5, which is equal to negative 1 over 25 once you let the limits approach. Looking at the fifth example, the limit as x approaches 0 of sine 3x divided by 4x. This is where we'll use an identity. Oftentimes you use identities for trig values. So the identity we want to use is this. The limit as x approaches 0 of sine x divided by x is equal to 1. How I knew that is because the question had a similar format. We just want to force it to be exactly like the identity. How do we do that? We need to have the same argument and denominator. Those need to be the same value. So right now it's a 3x versus a 4x. We need to make the denominator equal to 3x. How do we do that? We can factor out a 3x and then multiply times a 4/3 so that we don't change the value of the function. So we're using some algebra tricks here in order to change how it looks so that we can use the identity and simplify to this. So once we simplify here, our final answer is just 3/4. Now let's move on to limits at infinity. There are 3 common types of limits at infinity. The first is a top-heavy function. Second, same degree. Bottom-heavy function is the third. So these are characterized by their highest powers. Top-heavy functions have their highest powers on the top of the function or the numerator. Same degree functions have the same power. Bottom-heavy functions have the highest power on the denominator. So when we're working with limits at infinity, we have to remember some operations about infinity and working with infinity. So these few things here, negative infinity can be factored as -1 times infinity. Infinity minus infinity is not 0, but infinity. Negative infinity minus infinity is going to be negative infinity, and any real number divided by infinity is going to yield 0. These are important operations that will become really useful when we're trying to evaluate limits at infinity. This is a top-heavy function. Top-heavy functions can be solved by dividing by the highest power of the denominator. What does that entail? Well, we'll divide by x cubed in this case. So we'll be dividing the numerator by x cubed and the denominator by x cubed as seen on the screen. Simplifying this will yield this value. And once we do that, we'll let the limit approach infinity. So remember how to use infinity and what operations with infinity look like. So we have infinity plus 0 plus 0 plus 0 on the numerator plus divided by 1 plus 0. So that means that we're left with infinity over 1, which is infinity. So our final answer is infinity. This is a same degree function. The highest power is x cubed. And with same degree functions and limits at infinity, the answer is always the coefficients associated with the highest power. So the coefficient on the numerator is -5, and the coefficient on the denominator is 1. So if we divide everything by x cubed, everything that's smaller than x cubed, x squared, and x, and even the constants, will get knocked off to 0 once we apply the limit towards negative infinity. So that just leaves us with the coefficients of the highest power, -5 divided by 1, or -5 as our answer. So here's a bottom-heavy function. Bottom-heavy functions are nice because as you approach infinity, they always equal 0. So the limit as x approaches negative or positive infinity will always equal to 0. So let's just show this by dividing by the highest power. If we divide by x cubed, here's what we'll get. If we simplify it, here's what we'll get. Now let the limit approach, and you'll see that you'll have 1 over infinity plus 17 over infinity on the numerator. And you know that those both go to 0. So 0 divided by -1 will give you 0. Lastly, let's look at the limit definition of the derivative. So let's find the derivative using the limit definition. F of x first is x squared minus 7. Later on, you'll realize that using power rule, the derivative is 2x, and it'll be pretty quick. But we want to show this by using the limit definition. So how we do that is plug in x plus h first. That's how I get the x plus h squared. And then you would subtract just a regular function. And everything is going to be divided by h. So you're literally plugging in the derivative definition into the function that you're looking at. So once you do that, you want to expand as such. And then you want to be careful about distributing the negative. Distributing the negative will simplify to 2xh plus h squared divided by h. And you want to divide the whole thing by h. Then let the limit approach 0. So you get 2x. Now let's do g of x. So same thing. Plug in x plus h into the function and then subtract the function itself. Now, simplifying that, you have the 2's cancel out. Now you want to figure out what's the conjugate of the numerator and then multiply the 2. Both the numerator and the denominator. So that will look like this. And the reason is that you can simplify the numerator and get rid of those x values. Getting rid of those x values will leave h on the numerator, which will cancel out and look like this. Once you cancel out the h's, you want to let the limit approach. Doing so will lead to 1 over 2 times the square root of x as your final answer. Lastly, I wanted to give you all some resources that I found helpful. You can use your device to scan these QR codes, and they'll redirect you to the links, and you can check them out. Thank you for watching another edition of Course Foundations. I hope you enjoyed this video. Please subscribe to our channel on YouTube at UNTLC for more exciting videos, and check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.